it's not always possible to test the entire population. So we have this concept of inferential statistics where we test just a small portion of population, which we call as sample, instead of testing the entire population. So the steps involved in the process of inferential statistics are: first we draw a sample for which we have certain methods. Then we apply statistical operators on that sample. And the only statistical operator that we'll talk about in this video is mean. We'll calculate the mean of that sample, and we'll consider this mean as the mean of the population. So in simple words, we are drawing conclusions about the population on the basis of the sample. But the problem is that the mean of the population differs from the mean of the sample. The mean of the population is actually called parameter, and the mean of the sample called statistics. So there's a deviation, there's a random difference between parameter and statistics. And if this difference exists due to the fact that we haven't tested the entire population, then it's called sampling error. Now, solving this sampling error is the core of this concept of sampling distribution. So now the most crucial question that arises is how to fix this sampling error. So for that, let's first try to understand the pattern of this difference, the pattern of this deviation between the population mean and the sample mean, that is the parameter and the statistics. For that, first we'll take all possible samples from a population with the help of these formulas under different circumstances, and after calculating the mean of all these samples, what we'll observe is that these means are normally distributed. Now the most important question that arises is that is it true for all types of population that the means are always normally distributed? Yes, it is. It doesn't really matter what population you're working on, be it exponential or be it U-shaped or uniform or etc. etc. The means are always normally distributed. And when we say that these means are normally distributed, what we are actually saying is that there are some portion of these means which are actually lesser than the population mean. There are few that are larger than the population mean, and there's this one central value which is exactly equals to the population mean. So this central value is equal to the mean of the population. So now how to calculate the central value? Obviously by averaging all the means of the sample mean distribution, or in other words, calculating the mean of sample means. So as we can see in our example that now the mean of the samples is equals to the mean of our population, and the effect of sampling error is completely eliminated. So what we can conclude here is now that the mean of all the sample means is equals to the mean of the population, and this is what CLT, Central Limit Theorem, is all about. That if the sample size is sufficiently large, we don't have to test all the samples always. If it's sufficiently large, then the mean of all the sample means is equals to mean of the population. But now what do we mean by this sufficiently large sample? It actually means that the sample size should be greater than equals to 30. It should be greater than equals to 30. Now why is that? Look at this picture closely. We have taken sample from different types of population here, and as the sample size approaches to 30, as it comes closer to 30, the dispersion is corresponding to the bell shape of the normal curve. irrespective of the type of population. See, as the sample size is equals to 30, we have similar type of dispersion in the sample means. So due to this reason, it is said that the sample size should be sufficiently large. So we have talked about mean in this video, and we'll talk about standard deviation next time. So I'll see you in the next one. Bye bye.